Oh, hello, and welcome to Office Hours, the live version of the facility where good old Professor Kyle opens up his office door and you gotta take advantage of the time because all of you are failing the test and I need to change the curve on the test and I say the office hours are open for like 4 hours a week, but none of you comes in here and then now you all come in here and ask me all your comments, questions, corrections, comments about my hair and face, super chats. Oh, we're doing it all today. This week, of course, we'll be talking about also a number of segments of sciencey things that I thought were interesting throughout the week, especially some not so fun, and then some fun ones. It's been a rough couple of days, so we're going to be covering a number of topics. But in between each topic, I'll be taking it's live. We'll be taking your comments and questions and super chats. Super chats are enabled, so if you really want me to see something, I will do my absolute best. If I don't get to it, that's on me, but you're simping for science, so it's going towards a good cause and not just pizza rolls for me and my cat. I promise you. If you are new to this chat, I also have my security team from the facility in the YouTube chat, so no spamming, no all caps, no all that stuff, or else get out of here. That's just how I roll. And before we start, if you want to join the facility, become a staff member, get all my videos a day early, get on our Discord, join game nights and radio stations, and play me in an online Commander League. Oh yeah. And give me episode suggestions and all that stuff. You can go to patreon.com/Kyle Hill, as my security team is putting in the chat. I hope everyone is having a fantastic week so far. What year is it? It's Tuesday, right. And it's been, as I said, a rough week, but I believe our first topic is something that we should talk about because there's been so much speculation, misinformation, and questions about it, specifically relating to physics and that kind of thing. So let's move on to our very first topic before we get to any of your questions just yet. So, the explosion in Beirut. Let's just preface this by saying, of course, this was a tragedy. This is probably something, according to the information that we have right now, that could have been prevented. An amount of material was stored in a place that it shouldn't have, or it wasn't stored correctly, or stored unsafely, and this was a known thing to the government in Beirut, where, hey, we probably shouldn't be putting all this stuff near where all these people are. So, let's just get it all out of the way. There's a lot of politics involved here. There's a lot of charged emotions here. Protests are going on. So this is a very tricky topic. But what I want to do specifically is talk about the physics and the chemistry of this explosion to see if we can reflect back on this situation and see what we can learn from it. Not to take advantage of it, but just to more or less combat all of the misinformation that I'm seeing online about this. Like the size of the explosion. Was it nuclear or non-nuclear? Was it an attack? What was it made of? Blah, 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 blah. So we'll be going through it step by step. So as far as we know right now, this was an explosion of ammonium nitrate. Ammonium is NH4. It's a positive ion, and the nitrate part of that is NO3. So 3 oxygen atoms bonded to the nitrogen atom. And for the most part, this chemical composition is used as a fertilizer. Nitrogen is one of the key chemicals of life, and it's used in cycles of everything, especially plants. So it's a great fertilizer, and you can kind of supercharge the metabolism of plants by giving them more of these critical chemicals. So ammonium nitrate, usually a fertilizer. It was tested as a rocket fuel at some point, which should show you the direction that we're going. But when ammonium nitrate is manufactured, because of its potential to be volatile, as they say, it's usually manufactured with some sort of additional chemicals that make it harder for this combustion reaction to go off. Now, ammonium nitrate is kind of unstable in that it's happy in the atomic configuration that it's in. But if you were to add a little bit of energy to this system, whether that be fire or impact or another explosion or something like that, if you add a little bit of energy to this compound, it then, quote unquote, realizes it can release some energy and go down into a more stable compound. These compounds, quote unquote, want to be more stable. And so if they can release some energy to get down to that more stable state, they will do so. Unfortunately, when you have a lot of this, when you have, however trillion molecules wanting to do this at the same time, they release a lot of energy. in mass, and that creates an explosion. So there were images circulating online showing that this is probably fertilizer, but it may not be the kind. So it may not be the ammonium nitrate that you'd often use for fertilizer. It could be a different kind. There was images online of Nitropril HD, and if the photos are accurate, this is a knockoff brand of blasting agent. So this ammonium nitrate would act in a way like fertilizer with that nitrogen to fuel plant life, but it doesn't have those chemicals that are usually manufactured with it to help stop runaway reactions. So at the time I'm filming this video, we don't know how it started. We know that there was some sort of fire before the explosion, and this fire is the energy that we're talking about. Now, how can we be sure that this was, again, ammonium nitrate, not something else? How do we counter back against, like, oh, this was a deliberate bomb or some kind of, weapon? Well, you can actually look at, so chemists can actually look at the explosion, because it's almost unprecedented to have this much footage of an accident like this. I mean, think of the times that we're in, other tragedies, other large explosions or accidents or attacks. We're in a time where we have so many smartphones, so much technology. We're getting more and more footage of this than we ever have before. But chemists can and have look at this footage, and they see this blood red orangish cloud. Now, this cloud is indicative of nitrogen dioxide gas, and this gas is a well-known thing. This compound was also used in like signal flares and stuff like that. So this gas is a telltale sign that something like ammonium nitrate was used. Now, how much? Well, the estimates, according to Lebanese officials at the time of this filming, about 2,750 metric tons of aluminum nitrate were stored in a hangar there. That's 2.7 million kilograms. Now, when you translate that to, which I did, when you translate that to kilograms of TNT equivalent, so you translate it to trinitrotoluene, we get a better energy density example. That's at the far end, that's 5.4 million kilograms of TNT. So we're talking about 5 kilotons of TNT in the form of an explosion. Now, I'll point out how devastating this was because of the energy released from the chemical bonds. This was 5 kilotons worth of TNT. The total energy released in a thunderstorm is about 7. So if you took a monumental weather event and condense it down into a single explosion, you get something like this. Now, we know that this kind of explosion was not nuclear because of a couple of factors. Most notably, things that are missing from it. Electromagnetic pulse, fallout signatures, which would be easily able to detect the radioactivity afterwards. But also, this blast was about a third of the size of the blast at Hiroshima, well, the little boy bomb. So, and the video that I'm putting up on the facility this week is about nuclear war, and I just want to stress that the absurdity of nuclear weapons was that this explosion was the largest, like, peacetime accidental explosion ever. And it's not even a third of the most outdated nuclear weapon. And there's thousands of nuclear weapons. But we'll get into that later in the week. The other way we can tell that it wasn't a more traditional, quote-unquote, attack using high-energy explosives, high-velocity explosives, or something like a nuclear weapon, is because of the blast cloud that we're seeing. So what you're seeing right here, and this is maybe, not to be morbid about it, but this was the most, I'm using awesome in the original use of it. It's not cool, but it's the most awe-inspiring cloud like this I've ever seen form around a non-nuclear detonation. And if you look at the footage, you have this cloud that spreads out, like, and then you see a pressure wave kind of rip buildings apart. This cloud forms for a very specific reason. So when a pressure wave goes out from the center of an explosion, what the explosion is literally doing is pushing a lot of air out of the way in a spherical nature. And as it does this, the air at the front of this pressure wave is bunched up, right? So it goes and there's some differential between the atmosphere and the explosion, so it creates kind of like a layer, like a thick layer, pressure wave. That goes out. Now, behind this pressure wave is it has to be less air, right? A lot of air is being forced out of the way. Well, if we remove air from the interior of this explosion sphere, there's not as much air, and so the pressure of that air has to go down, right? Not as much air in the same volume. As pressure and temperature are related. So as this volume goes down drastically and nearly instantaneously, so too does the temperature. When the temperature does this, it can bring the air, if it's very humid air, like it is in Beirut, it's right next to the ocean, you can bring the temperature of the air down below the dew point. And so once that temperature cools even further from this rapid expansion, lowering of pressure, then water vapor will condense out of the air. And this was called a Wilson cloud when people first observed these physics, as in a Wilson cloud chamber used to observe nuclear energy physics kind of stuff. But this is a Wilson cloud like you'd find around an atomic weapon. But it's not. Because after this cloud, so we have this condensation cloud forming around this. But then there was a few moments later, you see this wave of air push stuff over. Now, if this was a more traditional high energy explosive or nuclear weapon, you wouldn't have a pressure wave like this. You would have a shock wave. A shock wave is when the pressure wave, I know it's confusing, but when the pressure wave gets so high that the pressure of the wave front is equal to or more than atmospheric pressure, and it's moving at the speed of sound or higher. We did not observe that in this explosion. We saw the Wilson cloud first. And so taking everything together, it seems like we have an accidental detonation of as many tons of material that were improperly maintained or placed, and we know that, well, we don't know for sure, but this brand of ammonium nitrate could have been a kind of used in blasting caps and stuff like that, so it wasn't the more safe fertilizer. And we know that this kind of fertilizer has fueled a number of accidents over the years. I believe it's like 47. So it wasn't, to the best of our knowledge, ammonium nitrate, 2,000 tons or so, almost 3,000, not a nuclear weapon, not an attack using conventional explosives. It seems like just a tragedy of safety. And sometimes that happens, and we need to do our best to correct for that in the future as best we can. And so all our thoughts at the facility go out to all the people in Beirut, anyone watching in Lebanon. It's a terrible accident. But with all this physics, I mean, it could have been a lot worse. I mean, that's the other indicator. It's like if there was an actual shock wave instead of just this pressure wave, you wouldn't have had just, a few thousand people injured and less than 1,000 people dying. You'd probably have much, much, much more. So this was absolutely terrible, but we need to learn from it. And the best way to learn about things, I find, is through science.